Hi, my name is George Batchvarov, and I'm from NCI, which is a Red Hat partner. And today I'm going to be presenting about a federal agency that pursue business logic at the speed of big data. You know, this is not your typical DevOps, microservices presentation. It's more of a, how we use the, utilize the Red Hat stack to solve a particular problem of a federal agency. So, with no further ado, let's move to the next slide. So let's first, I'll start with describing what the challenge was. So the mission of that federal agency, by the way, we're not, they didn't want to be, their name to be used, so that's why I'm going to be referring to them as the federal agency. So the mission of that federal agency, they wanted to modernize so they can actually provide better services to the, to the citizens and public by improving their experience. They wanted to achieve better compliance by separating the involuntary mistakes from fraudulent behavior and protect privacy and while protecting their privacy and prevent ID theft and maintaining a high level of security. When we went there, they described their business challenges as a follow. They had a huge data volume. I mean, as any federal agency, most of them work like if you want to deal with them, you have to fill this form, submit the form, and then they have to process and then render services, whatever the agency services is. So they were dealing with a really high volume of data. They actually process billions of forms throughout the whole year. And the rules and regulations are complex. The complexity is so high, actually it's a public fact that they had 74,000 pages of rules and regulations. And on top of that, it's, that is constantly changing. As an example, the rules grow with 140,000 words annually. And unfortunately, the forms do not arrive, equally across the year, but, they kind of fluctuate. And, as an example, 90% of the forms arrive the first 3 months, within the first 3 months of the year. And you can imagine with that high volume, as they were really concerned about human intervention and how to, how to minimize that, because otherwise, they have to scale up, which means, they have to hire people, and their budget's going to go constantly. We also, the current state, we looked at their current state, their infrastructure and IT. So what we noticed is that, they had actually a lot of legacy interfaces, and they were mostly operating in a batch mode, meaning they bulk the forms and then start running them through different system, and then bulk again, and then different system, and then bulk again in different system. The batch oriented usually, it's actually scheduled on certain times. See, every system has different times, so you can imagine how much overhead that actually adds to a processing of a single form. Dependencies are resolved only on a batch file level. The good thing is they actually had already kind of a service-oriented architecture, though in infancy phase. They were actually identified, a couple of common services, which were mostly a facade to a legacy interfaces like COBOL and assembler programs. And the last one was the one that is actually, I think it's the biggest problem that they had, is actually all the integrations and data level integrations, they were happening to a mainframe vSAM-based file. So every component and system that was working, they have to actually read from that file and write back to the file. So what were the disadvantages and the cons of their current state? As I spoke earlier, the batch-based processing injects a lot of overhead and delays into a processing of a single form. And you can imagine that actually they had that problem that a single form might take 3 months to process end to end, just because it, with all the overhead and batch processing. And sometimes if something goes into a exceptional phase where the human intervention is needed, it will stay there, and then later on injected back and going through the through the same batch driven architecture. And you can imagine that creates a lot of code redundancy. Sorry, they actually have high level of code redundancy, which leads to costly code updates, and it's error prone, because if you don't make the changes to all of the the business logic, then you're most likely going to get an error. And the fact that they actually work with that centralized vsum file, it actually started, it caused a massive data copying. So they were always, their network capacity is always behind. They always complain, oh, it takes a lot of time to, squeeze the data through and back. And of course, that ended up with a long-running jobs, and actually, you actually injected even more delays into the processing of the forms. So this is what they actually desired to get at. This is their future state that they wanted to get at. So they wanted to be customer-centric approach instead of form. They wanted to actually be able to, serve the, the citizens, and not processing forms. They wanted to be able to actually remember the goal to eliminate involuntary mistakes and separate them from fraudulent behavior. And the way they wanted to do that is to be able to address most of the data problems while the citizens were online or on their third-party software before actually it hits, and address the problems right when they are there, instead of giving them a notice that, oh, there's something wrong with your form, you have to fix it, and then creates financial complications out of that. They wanted to be able to process a submission on arrival. So instead of batching up, they wanted to be able to actually process the forms when they come and they hit the network. They wanted to be agile enough so they can maintain the complex rules and the regulations, and ability to scale up and down to meet the fluctuating workload. And of course, they wanted to control the minimize the human intervention, control the budget in that way, and that is like how did they thinking about achieving that is like they were saying like probably 80% of the forms can be processed without human intervention. So they can, and they wanted to be able to actually really flow the happy path, what they call this is the happy path forms. They wanted to flow them through without any need of people pushing buttons or approving to go through. Okay, so luckily we won the contract, so we went there, and this is the solution that we came up with. First of all, we went there and we defined the following principles. We decided that it's best for there because of the volume of the data that we have to actually use a massive parallel processing platform with a shared node architecture to achieve maximum level of scalability and parallelism. We wanted to process everything in memory. We didn't want to have the code to reach out to the data and come back and squeeze data through the network. Keep it in memory. And third one, that's my favorite. Actually, I put it on my Twitter. It's bring the code to the data instead of data to the code. The code is much smaller, much more static than the data. Why would you need to, fly 1 terabyte of data to, so in some processing node and then fly it back into the repository? Organize the common functionality as microservices. Even though that was not part of our scope, we actually said that that's a beneficial to them, and we all now know all the benefits of using microservices architectural pattern. And the last one is use business process management software for integration. That's actually the key point. Why? that goes back to the agility, for their agility to be able to actually respond to changes in the, in the business logic and the regulations. Now, with their legacy code, what happens is, the regulations change. Then a bunch of bunch analysts sit down and they write the requirements, and these requirements are passed over to the developers, and these developers do COBOL or assembler or whatever, and they put it in, and then this is how they implement it. With the BPM though, it allows the actual business analyst, instead of talking to developers and they actually do the actual business logic right there using the software. Building workflows. I mean, and we'll get to the actual, Red Hat software stack that we used. Using all these principles, this is the logical architecture we came up with. You can see that in the middle, we have the in-memory MPP platform. And every form is actually a different applications. Every form is a different application. And the application has a bunch of business workflows that are exposed to the, whether that's going to be the web UI or the third-party vendors through an API that can actually process the forms using microservices and human task management. The critical point of actually using a BPM software, I mean, some people say, BPM is an old thing, and I actually would argue with that, because using BPM it actually requires a certain discipline, and if everyone follows that discipline, actually BPM can be very successfully deployed within an organization. And the way we achieve that is that, imagine that workflow is actually your sentence. Your data model or the business model is your words, and the microservices is your verbs in the sentence. So this is how you form a sentence. I've seen actually a misuse of a BPM where actually I looked at the the actual workflow, and the people the developers were actually writing database locks within the BPM. And that's wrong, because if you expose that to the business analyst, they don't know what the database lock is, or how to open a connection to So that's why this complexity is hidden within the microservices, and the microservices is a business verb that the business understands. For instance, submit a form, or verify a form, right? That's how it actually BPM is actually very useful, because now the business can write it, because they know their workflow. They know the first thing I'm going to do is I'm going to check the validity of form, then I'm going to do a financial check, and then I'm going to do or if it's wrong, then I have to send it to this, and this is how they actually build it up. They don't have to write any line of code, right? Everything is on a business level. So the software stack that we used is the MPP platform. For MPP platform, we use JBoss Data Grid. So it's in memory. That's a memory software, memory cache from Red Hat as an API layer, and microservices mocks. Actually, because again, we didn't have to write the actual services. We actually had to write mocks. We use JBoss Fuse. For BPM, we use the JBPM. For persistence database, we used Oracle. That is something because we actually used Oracle because that was a constraint from the federal agency. They just had to use Oracle, but we could have used any database. You will see that when we moved the transactions and the processing in memory, actually the database becomes irrelevant. It's actually only a backup system where you put stuff, and we'll actually get to that later on. So that's why we could have used easily Postgres or any other lightweight database. Human task management, we used part of JBPM, which is called the Business Central. There's a lot of out-of-the-box features. I've been in other accounts where I see, multiple teams developing features that are out of the box of Business Central. The reporting, we used again another out of the box feature of JBPM Business Centrals. They actually had out of the box dashboards that were showing what's the status of the workflows and the forms, so the business can actually see what's happening, and if there's a problem, they can react to it. Monitoring, we use the JBoss operational network, John, which is based on SNMP and JMX. And of course, all components were running on JBoss Enterprise Application Platform, the EAP container. So let's just dissect an application. So you see that we have the workflow. The workflow is actually we created a little bit of an abstraction here. The workflow, the JBPM runs actually embedded in JDG. So for us to be, and since that worker gets executed on an event, we had to wrap it up in something called worker. And so the worker is just a wrapper that actually executes a workflow. So here's what happens. We have something which is called bin, and if someone wants to invoke a workflow or a worker, for example, it's an interactive service, what they're going to do is first of all, of course, they're going to write into the business model pool. So the business model pool is actually the cache where all the context gets collected. You can imagine the first thing that's going to come is the form, and then the different microservices is going to start gathering different information like financial, background, fraud, and all this thing is going to put this and start building a case. And that's what it's called the business model pool. So what a service is going to do is the first thing is going to actually write here to the business model pool, and then it's going to drop a token. And the token is a very small data that actually only has the case ID. And that's going to, we actually listen to that cache, and that listener is going to wake up based on that token, and it's going to start the worker, and the worker is going to use the business pool right back if it has to, and then return back when it succeeds. And that's for a synchronous service, like for synchronous service, interactive services. Submission service is more of a like asynchronous service. So for instance, when they're ready and I say I'm ready to submit my form, and then submit, and then there's a process that starts that has to actually process the form. Then what happens is we write back to the first thing we do is write to the business pool and then drop the token, and then that's going to automatically start the worker. And you can imagine that actually we can have multiple workers, because when this worker, if there's something happens, it might decide that the business logic tells that they have to wake up another worker. So they're going to drop bin to another worker, and that's going to process the form till the end. And of course, the last type of service is just read service. What's my status? Where is my form? So for those who are not familiar with JDG, I'm pretty sure those who are familiar, you probably not, you already know that. But the way JDG works is that it actually uses multiple machines, and it actually stores the objects in the cache. And all these multiple machines, they work as a cluster, so the cache looks like a one big pool of cache. And for high availability, what they do is they actually replicate the object. So for instance, if someone wants to write an object in the cache, it's going to pick a primary node. JDG is going to pick primary node, actually going to write it here, and then replicate to a secondary node. And that's when the transaction of writing ends. You can actually have, you can specify the number of replicas you want to have. The bigger is, the more secure, secure your system is. So if something happens to one node, I'm still have all my data. I haven't lost anything, right? If I'm replicating twice, if two nodes go at the same time, and they have two copies, I still have one that is there. So of course, also we have remember that I told you that the database is just a persistence layer. So what happens is we use that right behind technique, what happens is this writing back to the database is not part of the writing transaction, but it just accumulates a couple of transactions, and when the buffer fills up, it actually push it to the database layer. And so this is good if something drastic happens. We can all start again, and it's going to warm up from here, and everything is still there. We used usually the out-of-the-box solution stores the data serialized. So serialized data, it's very difficult to write queries against. So that's why actually we use the JPA map right behind, which actually relationalize the data. So the reason we did that is because we wanted to be able to run different types of reports against the data. So this is how the parallelism works. The way JDG stores, the way JDG decides what node they're going to store the data in, is they do it based on a hash function. So, every object has to have a key. So they actually run the key against the hash function, and they decide to what node they should go. And so what happens is, here's how the parallelism works. So we have a service proxy on top, and load balancing here, we do it on a round robin. So let's imagine that we have a object that gets stored here, right? Because the hash function returns here, and then we call the service, and let's say the round robin actually called it here. So this is going to drop a token to the in a bin, and the bin is distributed in the same key, which means that's going to wake up the worker here on this node. And the worker, see, the good thing is the data is here. I'm not copying it across. So every time I'm running running stuff about this data, it's always going to be running on this host. And with the distribution, once we start getting a lot of forms, and it's the hash function is good function, and we usually actually tested, and we saw that we found a key that actually guarantees an equal distribution. We get actually a very good parallelism. So how we actually integrated with microservices? So like I said, the workflow is just a business level, and they actually call the microservices, although we do not call them directly from there, but we use the facade. The reason for that is that if the microservice is down, you don't want your code to kind of start erroring out, right? So that's why we had the facade, and when it's down, it just returns an error and then does something, so the code doesn't die. So that's why we have the facades. And the good thing about the facades is actually we originally run this in Amazon, and when we were ready, we moved into the IRS, and we started integrating with the actual services. I thought I said what the agency name, sorry, and that was actually a very successful thing, because the only thing we had to work on is this, the facades. All right, BPM persistence. We use the out-of-the-box BPM persistence. So what BPM persistence is, the workflow, you can imagine it has a context. So when it's running, sometimes when you start getting a lot of data, and if there's a lot of forms that actually go in a human task or some long-running asynchronous tasks, and your memory starts filling in. So once you get to a certain level, then what it does is actually it evicts the one that is not active, puts it in the database, and if when the asynchronous transaction finishes, then actually restores it from there and returns. I have to go through these slides a little bit faster. So the reporting is nothing interesting. The good thing is that this architecture actually allows both integration patterns, and there are two competing integration patterns: orchestration or choreography. I mean, I'm not here to for people who are architects, what's the difference. We originally were thinking about, hey, we're going to do only choreography, and that started a religious war, and we're like, okay, you know what, we'll support both. So like I said, the choreography, the interesting thing is when I was mentioning that is when this worker gets to a point of where they say, oh, I probably have to invoke that other, they just invoke that other. And when that, so every worker here has its own script. It's like a theater. Like every actor has a script, and they act on triggers. DevOps, you're all probably familiar with that. It's really not interesting. It's the standard stack. We we use Docker, Docker to be able to actually stand up quickly new instances if there's a workload. It was actually an auto-scaling app. We used Bamboo instead of Jenkins, but it's pretty much the same thing. Confluence and Wikipages and Jira for our ticketing. Now, I want to get to the most interesting part, the results. Right, so this is the AWS architecture that we used. We used 3 servers for the JDG, and we used it in the library mode. The JBPM was embedded, and we had Apache CXF for the facades, and the key remote API to actually call the human task on this box here. So this is the physical architecture that we used. The test plan was like this. Our pilot logic represents approximately 10% of the logic related to a medium complexity form. In each test, we actually tried to find the breakpoint, what I call the choke point. So what we do is we increase the load, and once we start seeing degradation of performance, that's what we call the choke point. And then we actually started measuring that for different number of nodes. The idea is that we wanted to prove to see whether this has a linear linear scalability. Sorry, and this is the result. So remember the first test when we run with a single test, we figured out. So this is forms per second. We figured out that actually the way we increase the load is we create a thread that simulates a person that is doing something and submitting. So we found that with the one node that was the optimum. See, the performance increase, and all of a sudden it starts degrading. By the way, the good thing is the degradation is not really killing the system. What happened is it keeps working, but you're getting worse performance. Right? So that could have been used, like if we have an auto-scaling like that is meant to be, you can actually, when you start getting degradation of performance, you can start bringing up new nodes, right? And here's the test that we did with 1, 2, 3, and 4 nodes. And watch this, 20, 20, 20, success. It's a linear scalability. This here, translates into 300 million a month if it works 24/7. Which is pretty good. I mean, we can cover, even though that form that we used was a medium complexity, not really that heavy. This here is an important thing. When we were discussing with a federal agency, what is the level of security what is the level of high availability they care about? They was like, oh no, we probably want to maintain 3 copies. That's what they call the factor of 1 means 2 copies, the factor of 2, 3 copies. And all this tests that we did, it was factor of 1, which means we only maintained 2 copies of the same data, right? And we noticed that if we increase the factor, we're paying 7% performance penalty for increasing that. So, any security is going to come with a penalty, of course. And that's it. Thank you very much. Do you have any questions? I hope this was helpful. Like I said, it was not DevOps, it was not microservices. It was just using out of the box Red Hat software stack to solve real problems. All right, thank you.